Now we're going to talk about the different states of matter. And this is fairly elementary in the sense of what the states of matter are, why they assume the state that they're in is, as in all things with science, there's usually a very deep explanation that gets into quantum mechanics and stuff like that. But at least we can get some understanding from, this idea of just the fact that everything's made of atoms, and all of these atoms have a certain kinetic energy. And we can throw in a few more facts about matter and get to an understanding of these different states of matter. So there's 4 states of matter that we experience on an everyday basis. We have solids, liquids, you guessed it, gases, and plasmas. And you may not think that you experience plasmas regularly, but in fact you do, and we'll talk about that. Now, in a solid, you have the situation where the atoms are bound strongly to each other, and not all solids have a regular pattern like the one I'm drawing now. This is a very regular crystal, and there might, let's say it's salt, so it's sodium chloride. So you would have, here's your sodium atoms, and then the bigger atoms are your chlorine atoms, okay? So that would be sodium chloride. It's a very regular square crystal. But your solid are, you can have things like proteins, for example, which I don't know if we talked about that at all this semester, but in something like a food is made of proteins, which are very complex molecules, and they have a definite shape and size, and all the atoms are in a particular place within that molecule. Or an ice crystal, it's a more complex crystal than the one I drew, but all the atoms, the idea is all the atoms are in a given location in relationship to one another, and they're bound to each other by intermolecular forces or ionic forces. In the case of this crystal, it's all the same thing in the sense that there's a force, and I'll just depict it by drawing a little spring. There's a little spring between all the atoms, and they're all held together, and they can't go anywhere. They can vibrate, they can flex, but they can't wander throughout the crystal. So they're really stuck together, and the only way to move an atom from a crystal is, or from a solid, is to break the solid. If you break it, then you can move an atom from one place to another. But like I said, the whole thing can squish, it can compress a little bit, it can vibrate. It can't compress much, all right? So that's something to be careful of in the terminology. They'll say that, the solid is not compressible. Well, okay, it's not compressible, but very much. But indeed, it can be squished because you can cause those bonds to change shape a little bit. And depending, some solids can squish more than others. Okay, so that's your solid. Now, a liquid is different. Let's talk about a liquid. In a liquid, here's your different, again, we'll just use, let's just consider that these are water molecules. I'm not drawing the whole, well, okay, I can even draw the molecule. I'll draw, here's the little hydrogens, hydrogen and oxygen on our water molecules floating around in the water, being water. Okay, so there's our water molecules floating around. Now, in in this case, there are still forces between the molecules, right? In this case, and in water, you have the force of the hydrogen bond, which is a weak force, relatively speaking. It's not as strong as an ionic bond or a covalent bond, but it's a force nonetheless. And the force attracts the hydrogens to the other molecules. So you can still draw these springs, but in this case, it's weaker. And the molecules are free to move about. So this molecule, maybe it's bound to this one now, but it can kind of, because of its thermal energy, start to move and change the molecule to which it is bound to. So you end up with a situation where the water has a fixed volume because of these forces, but the forces aren't strong enough to keep the atoms from moving at all. So that's where you get the situation of a liquid, where the atoms or molecules can move around, but they're not going to be totally fixed in their position. So that's a liquid. And again, the only other thing we need to know, besides the fact that there are these particles called atoms, and that the temperature is the average kinetic energy of the atoms, the only other thing we have to know is that there's a force between these atoms, and the force, you should recall, is based on the model of the atom, which is that the atom is comprised of, you've got your positive and neutral particles in the nucleus, and then you've got your electron on the outside, and the electron is negative, and the negative charges of different electrons attract one another. And let's take a look at what happens in a water molecule, for example. Okay, let's take a look at a water molecule. So in a water molecule, you have your oxygen, and your two hydrogens, obviously, that H2O. Now, the oxygen is very electronegative. So what happens is, if we look at this, I'll just draw the oxygen atom again as it is, but then we'll draw the hydrogens. You've got your positive nucleus on each hydrogen, and then you've got your electron cloud. Well, what happens is the hydrogen electron cloud gets shifted towards the oxygen atom, because the oxygen wants the hydrogen's electrons. So again, here's your positive, your proton of your hydrogen, and then your electron cloud ends up kind of getting shifted like this into the oxygen atom. That's your electron. Well, what you end up with is a structure that has a positive charge on the outsides here. So you've got these two positive charges. Well, here's another water molecule. There's the oxygen of another water molecule. Well, it's going to want to be attracted to that positive, to that proton. So you end up with this force here. I'm not drawing my force very well. Sorry, folks. You end up with a force of attraction. These two things want to get near each other. And that's your hydrogen bond. And in water, you have all of these hydrogen bonds forming and breaking all the time, but it ends up giving water a lot of very interesting properties, such as its high surface tension, and one of its most important properties is it has a very, very high specific heat. In fact, the highest of all known specific heats, and that means it takes a lot of energy to get a kilogram of water to raise its temperature 1 degree takes a lot more energy than to raise any other substance that amount. And the reason is because of that very strong hydrogen bond in water. So that bond is responsible for the liquid and, well, actually it's responsible for all of the different properties of water. But in any case, that's an explanation of one type of liquid, which is water. You have these bonds forming and coming and going, and in all liquids, there's some kind of bond that's causing the molecules to want to be close to each other, but not strong enough to keep them in a solid lattice. Now, when you get water cold enough, this bond, because the thing that's breaking the bond is the kinetic energy, or the shaking of the atoms, which is depicted here by these arrows. If you get it cold enough, that movement starts to decrease, and then those hydrogen bonds can take over, and then you get an ice crystal forming. And it's the same for all liquids. When they're becoming solids, you are decreasing that kinetic energy, and all of a sudden you're able to maintain those crystalline structures long enough for a large crystal to form. Okay, we will continue next with gases.